Recording in progress.
All right, guys. So we're going to start talking about exponential functions and their graphs. Let's see how far we can get today. I think I could get all this done, but if not, then we'll have to table till Monday. No, the first part of the notes. The first part of the notes is 8 pages. Yeah, I know. It's a lot. All right. So first off, what's an exponential function? An exponential function simply is something that follows this: y equals a times b to the x, right? So that's your base. That's your exponent. And that's your initial value. And as a whole, b to the x as a whole is called a power. So I'll make sure we're clear on terminology. Like x is not a power, b is not a power. B to the x as a whole is called a power, where b is the base of the power and x is the exponent of the power. Okay, so we want to make sure we're clear on that terminology. So how are they similar? X squared and 2 to x, both are powers, right? They're both powers. But how are they different? X is the base for f of x. 2 is the base for g of x. So your exponent, sorry, your variable is the base in the power function, but an exponential function, the variable is the exponent. So hopefully that makes sense there. Definition again, have it right here. I kind of already did it for you guys. A is not 0. B will be positive. You never do a base that's negative. It just gets really wonky if you did. Plus, you might be rooting. If you have a fraction exponent, that's kind of weird because it'd be imaginary. So we always make the base positive. If it's 0, forget you have nothing. You have y equals 0. And of course, A has to be non-zero because again, you have y equals 0. A could be whatever because you could stretch it, flip it over, do whatever you want. That's all good. Questions on that part? All right, let's look at these here really quickly. Which of the following is an exponential function? If yes, identify the initial value and the base. Easy peasy. Yes. No. Yes. Yes. And no. So clearly the initial value is 1. And the base is 3. Here initial value is -2. Base is 1.5. Here initial value is 7. Base is 2. And e throwing into a loop, that's just a constant, right? Whatever 6 to the pi is, like some crazy number. But it's a number, not a variable, right? So I don't know. You might be right. Yeah, probably that sounds right, because 6 cubed is 216. So it's a little more than 216 times 5. Catherine, go ahead. Oh, duh, you're right. You are so good at correcting me. Thank you. Awesome, Catherine. Thank you. Yeah, my bad. That was 7 times 1/2 x. My apologies. Yeah, base is 1/2. Okay. Now for example 2. That's easy. G is 0. That's 1. 1/3. √3. And 1 over √27 or 3√3. I think. Yeah. -3. 6. -3 over √2. I think. Is that right? Yeah. Oh boy. You are correct. Yeah. And that one, I don't know. 1 over 2 √2. Yeah, it's one over root 8, or 1 2 root 10. You could flip it. Yeah, yeah, that's right. Yeah, go ahead. I made a mistake. Do you have a question, or you want to correct me? No. All right. I'll pause so you guys. Let's keep moving. Next one, the graphs. The next one's let's be great. Graphs. Let's do that next. Yeah, if a b is bigger than 0, sorry, b is bigger than 1, that's growth. If it's less between 0 and 1, it's decay. So these are all growth functions. You guys should know that. We won't do this in the graphic calculus. I think you guys get the idea. So which point do they all have in common? They'll all have 0, 1 in common. And actually 1, b. Because the b values are different, clearly, but they're all going to touch 1, b. So let's do red for that one. Green. Blue. No attack, we'll do yellow. Easy peasy. Do 3, 4, 5. Green. Blue. I know it's kind of hard to draw. Bear with me here. Okay. Anyway, I didn't do the best job drawing it, but you guys get the point. The domain is all real. The range is 0 to infinity. 0 is not included. It's always increasing. It is continuous on all real numbers. There's no symmetry. The boundedness is y is greater than 0. You can't go below 0 for y. That's called boundedness. Questions so far? Nothing really. Yeah, I think you're being a little more explicit as to what is being bounded by. Like if you have a logistic function, I'm not sure if you guys have seen that. We might broach that in this unit. Logistic functions kind of look like this here, where they have actually 2 asymptotes, 2 horizontal asymptotes. But yeah, I guess it's the same thing. Boundedness and range. Yeah, I don't really see much of a difference. Yeah, I don't know. Yeah, Kevin. It's like same thing as range, for the most part. It's kind of like what is being bounded by? Like what is, put this way, is there a basement? Is there a floor? Is there a floor? Or is it just wall forever? Or is there a ceiling? Right? Is there a ceiling? So it's kind of like that. Asymptotes, pretty obvious. Y equals 0. Extrema, there's none. M behavior, the limit as x approaches negative infinity of f of x is going to be 0. And then the limit as x approaches positive infinity of f of x is going to be infinity. Okay, does that make sense? The end behavior, that's the part I kind of care the most about, because that's kind of more the calculus implication of it, which is what we're working our way towards this spring. So okay. Next part should be pretty fast too. Obviously the base is less than 1, but greater than 0. So what do they have in common? Yeah, except for what? The characters for the exponential are the same as the characters of exponential growth. Oh, well, obviously it's decreasing. Also, the limit as x approaches negative infinity of f of x will be positive infinity, but the limit will be 0. They're all going to touch at 0, 1. Yeah, I'm kind of fudging this, guys, but you get the idea, right? Yeah. Anyway, that's what's happening. Okay, transformations. Don't overthink these. Excuse me. So compare it to the parent function, y equals 3 to the x, y equals 3 to the x. Okay. So generally speaking, you think of it like this: y equals a times b, c parentheses x minus h. Well, I'll make that a little easier to read. Plus k. Is there a k value here? It's 1. And there is a coefficient in front of x, it's 2. So let's make the table for the parent function. 0, 1, 1, 3, and I'll do -1, 1/3. Now for the new function, how am I going to impact y? Plus 1. So 2, 4, and 4/3. That's kind of part of the cloud method, right? Because you have to add 1 to these. What do you do about x? If there's a 2 being multiplied, you do what, sorry? You divide by 2, guys. Yeah. Yep. 0, half, -half. And there's a vertical asymptote right here. Yeah, and you have a horizontal asymptote y equals 1, right? Domain is all real. Range is 0 to, nope, 1 to infinity. Why don't you guys try B? Try B. I'll freeze the screen. And C as well. Let me zoom out a tad. Then we'll move on to E, where the base is E. You have a visor after this. I don't. Yeah. Yeah.
always zero concurrent function.
So, yeah, sure, yeah, go. Okay, I'm almost done here.
Oh, it's negative.
All right, let me unfreeze my screen. There we go.
You took the AMC beforehand? You have to qualify. Yeah.
Yeah, I took the AME once in high school and it was so hard. It's a competition. The one after that's even harder. Then you're just awesome. You're like at Good Will Hunting or something like that.
Understand what happened, what we're saying.
Right. It's so abstract. I know. It's elements. That's called elements. Yeah. Yeah, it's a tough test. Yeah. Anyway. Okay, guys. Here are the answers. Any questions? We're okay? We're good? Okay, so the third one actually is a growth function because you're flipping the base. The base right now is decay, but because of negative exponent becomes 4 to the x. So actually it becomes growth, believe it or not. B is a growth function, but it's flipped over because of the reflection. And of course, I adjusted the table. So I did the parent function first, made the adjustment. I didn't show the adjustments, but I think you get the idea for B. You're going one left, multiplying. So you have to add 1 to x. Sorry, subtract 1 from x. And then, of course, multiply y by -2. For C, we have to use multiply the x's by -1 and subtract y's by 2. Okay, let's keep on moving. Natural base. In case you don't remember, guys, I'm sure you guys did it in Ms. Wong's class last year, but when you have an expression, 1 + 1 over x raised to the x power, it's called Euler's number. This guy Euler discovered, if we have this and x gets really large, it actually converges to a certain number. It's roughly 2.7. I think it's like 2.718, if I'm not mistaken. And there's a few more digits. I mean, not a few more, infinite digits. This is an irrational number, just so you know. So this is an irrational number. Okay, let's keep moving, guys. So it's called the natural exponential function. E is considered to be the natural base. The letter E is initial of the last name Leonard Euler, who discovered this. Does have special calculus properties, which kind of simplifies many calculations, but we'll cross that bridge later with the calculus part of it. But when you do like things called derivatives or integrals, which you'll do in calculus, it does simplify the problem significantly. Even when you're modeling stuff that have exponential nature, E does make the math less crazy, just so you know. So it is kind of a neat number. If you graph it, it's real easy. It's going to cross at 0, 1, right? But make a quick table. Definitely 0, 1, and 1E, which is 2.7, right? I just said that. So yeah, it's not any different. So y equals 0 is the asymptote. The domain's still all real numbers. The range is y is greater than 0. You know, all these things we know. We know these things, so we're okay? Okay. Next up. The y-intercept is 0, 1. That doesn't change. If you have e to negative x, it's just you flip it. Not a big deal. You have this. 1 over e is like 1/3 roughly. Something like that, like 0.3, I think. So again, you have 0, 1, 1, 1 over e. What is 1 over that number anyway? Yeah, 0.367 roughly. 0.368. Asymptote's still the same. Right? It is a decay function, just so you know, same properties. Not any different. Y-intercept is still 0, 1. Sorry to delete that quickly. Do you guys need to see the other stuff? My apologies. I hate when teachers do that when I was in college. Sorry about that. The y-intercept, we know 0, 1 at the bottom, so that's easy. Okay, we're good? Yeah, pretty straightforward. Okay, we're humming along here. And when do we get out, by the way? 55? 11, good. Yeah, we got time. We can get this done. I'm confident. All right. So determine the exponential functions for the following. These are kind of cool. I like these problems. So let's figure out g of x and h of x. And it's also, yeah, let me just make another area for h of x. Okay, the initial value is when x is 0. What's the initial value for g of x? 4. And what are we multiplying by over and over again? 3. Yeah. You're tripling every time. You don't actually have to do any work because it's pretty obvious for the but now if I gave you, say, x equals -2 is 49, so x equals 2 is 36, then that might be a little more tricky, right? Then maybe you have to do some algebra. Maybe 22 and get something here by -2, and then kind of do some sort of substitution or a combination of equations. But when you get in a table this explicit, it's pretty easy. Like, what are you going to say for h of x? What's your initial value? And what do you multiply by? 1/4. Yep. Every time x goes up by 1, y is multiplied by 1/4, right? Okay, this one we have to use a calculator. The popular San Jose in 1990 was this. In 2000, it was that. Obviously, something very significant happened in the mid-90s, the dot-com boom. Now it's even bigger, right? So assuming the growth is exponential, let x be the number of years since 1990. Okay. So let's answer some questions about this. What will the population be in the year 2050? Okay, not hard. Very easy. Y equals a times b to the x, or y equals 782,248 times b to the x. Okay. Now, how am I going to solve for b? What am I going to do, guys?
I would divide y.
Yeah, let's do 894,943 times b to what power, guys? 10, perfect. So b to the 10th equals that quotient, whatever that is, 894. 1.114. So 1.144 raised to the 0.1 power. So it's about 1.4% increase. I didn't say, but what do you think I did?
Did you tap through or did you-
I 10 through. Yeah, thank you. I 10 through it. Yeah, that's what I did. Does that make sense? 10 through it? Totally. 100%. Yep. So now I can figure out the population in the year. Assuming that the growth stays about the same. And I have to put 60, right? Because 2050 is 60 years after 1990. So if I work that out, 782,248 times that raised to the 60th power. Oh boy. 1.75. I don't think you support that many people. No, 1 million people. Almost 2 million. Well, Science is has a lot of area. But just out of curiosity, right now was 2024. So let me repeat that calculation, but raise it to the 34. Yeah, so if I do it to the 34 power for the year 2024, it says about 1.236 168 million people.
So it says, oh, in 2020 there, a little over 1 million.
Jose.
Oh, it went down. Siri, you
Yeah.
what? That's not right. That's not 1.8 people.
They can learn
Yeah, I don't know. It seems a lot to me, but whatever. Okay. Well, I don't know. All right, let's keep moving, guys. When we'll surpass 2 million people. Real easy, guys. Guys, quiet, please. So you're just gonna do this. 2 million. I think Rev City's got too many people. It's always crowded. Right? Totally.
They don't have the target for the movie theater or downtown.
Or restaurants.
Yeah,
Most of the people have seen it.
Okay, I'm getting this. And then you can say X equals log base. We haven't talked about logs yet, but I'm pretty sure you guys can handle this because we're gonna talk about logs next week. You guys are comfortable with logs? Yeah, not hard. So alpha window log 1.014. And it might be off the tag because I am rounding along the way. So it's going to take about 67 years after 1990. So about the year 2057. So about 34 years from now, or 33 years from now. Right. By the time the 40 have a new stadium. So who knows where we'll I'll be 80 years old then. So I'll be an old man. Okay. Next up. Let's talk about growth models. What was that? 2014. I know because I've had student tickets and it cost me a lot of money.
My class.
Right when I finished? Okay. I think they could have done a better job with it. My wish was they would play at Stanford Stadium for 2 years, bit the bullet, lost money in seat revenue for a couple of years, and then build a beautiful stage like by the water. And build like a nice development area. Yeah, Sarasota just can't get this act together, but that would have been my dream that if they had done that, but didn't happen. So, all right, yeah, it's just a better spot. But well, the tailgate stinks there. It's like it's not even great to tailgate. Like it's not the same as Council was. It's it's like fragmented too. It's like you're like you're an office park, but you can't tailgate. You can't have barbecue there. It's just dumb. Yeah. They didn't think that one through, but
I did not think of.
no, they just wanted to appease the Silicon Valley elites and yeah, whatever. Anyway, I got my issues with that. All right, the enrollment student heart, guys, quiet, please. Grows 3% every year. Let's say the student, guys, quiet. Let's say this current population is 550. Find number of students enrolled at each time period indicated below. What pattern do you notice? So right now you got 550. And you do 550 times 1.03. Then you're gonna do 550 times 1.03 squared. Then 550 times 1.03 cubed. In general, it's 550. 1.3 times 1.3 raised to the t power. So what this is, the usefulness of this is like, it's say like finances is very useful, right? Like say you've got like money in the college fund or you're investing money, right? And you want to how much money you have after 20 years. I mean, you guys have been in college in a year or two for now, but you know, if you have like a 5-year-old kid and you've been saving for them for 12 years, you see maybe 10% growth in the stock market. Maybe you want to figure out, hey, how much money do I need to add to my kid's college fund so they have maybe $250,000 by the time they graduate high school. So you use exponential modeling for that. That's what's happening here. Because you're adding on over and over again. Of course, there's yet another wrinkle we could add. What if you keep adding money along the way? That's another situation, which I don't know if we'll get there today. I have to look in the notes. But this is very simple. You start with some money and you just let it sit and it grows as time passes, right? Assuming money or population, you know, whatever you want to talk about. Are you good?
Oh,
Okay. So just small changes in variables. P sub 0 is called like, it's usually we use that for like initial population. So that's the initial population, P sub 0. Right? And if your rate's bigger than 0, that's growth. If your rate's less than 0, that's decay. So R is the percent growth or percent decay. So Atherton actually has decayed, mainly because a lot of people die in their homes. They live there forever. And that sounds morbid, but you know, it's very expensive to buy Atherton. Some people just live there forever until they kick the bucket. So they decay, exactly, right. Actually, really interesting. I was looking at one real estate. I love looking at real estate. So a former teacher, you know, one of the ghosts is called Donna. So that's named after a former teacher that used to work here, Donna Bilboa. She passed away last year. She was 9 years old, but she owned a house in Atherton that she bought with her husband in 1973 for $100,000. And I taught her grandson, so I went to her memorial and I know the family quite well. And they recently sold it. Her daughter sold it 50 years later. So again, 1973. $100,000. Richard Nixon was president. There was Watergate. We just went to the moon 4 years prior. We were in the Vietnam War. Totally different time frame, right? And she was working at the school, by the way. This teacher. How much do you think the house sold for last month?
oh.
So, well, not lower than 15. No, did not.
Oh.
It was in Lindenwood, and past the gates, and it's Wisteria Lane was the name of the street. And it was 1 acre, about 1 acre lot, 2,500 square foot house, three bedroom, 3 baths, like a very standard $6 million. $6 million, crazy. And so I was gonna tear it down and build a monstrosity. Anyway, yeah, it's interesting. And actually, you could use exponential modeling for home prices. It's a fascinating topic to use it for. But anyway, what are we doing here? That's decay, guys. That's growth. Percentage rate, that's 0.3%, and that's 0.24%. So the town of Alta has
Decayed by 0.24%. So do one last that number, which is 0.0024. But remember, percentages are divided by 100, right? So you have to, when you have a decimal, 1 minus that is 0.0024. You have to multiply decimal by 100 to get this percentage. Here, subtract that by 1, which is 0.003. It's actually a 0.3%, right? And Menlo Park has grown, but
you know, it is Menlo Park. It is also very expensive with Menlo Park. But anyway, now Redwood City decrease. I don't believe that. Really? That doesn't make any sense. We're gonna say it's increasing. Yeah. Yeah, I totally don't believe that. Well, let's say it's increasing. Let's make this realistic, guys. That's dumb. Yeah, totally. Like they built all those apartment buildings along like downtown. Okay, so you got 73,114 people right now in Redwood City. I think it's more than that, but and you do 1 plus 0.0303 raised to the fifth power. And you work that out. So yeah, there you go. Not that hard. Hogan starts a new hobby of collecting grasshoppers. That's kind of weird, but anyway. He starts with 3 of them. They double every day. How many do they have after 30 days? Okay. So he starts with 3. If they double, what's going to be your base? And raise to what power? Or 30, right? 2 to the 30th power. He's got a crap load of grasshoppers. Hold on.
Oh, what a man.
$3 billion grasshoppers, yeah. Okay. Yeah. Actually, it's $1 billion. It's $1 billion, yeah. Yeah.
This could take down like. Yeah.
Yeah. Yeah. All right. Kate is doing research in biology. The bacteria population doubles every 6 hours. Starts at 200. Okay. Now this is a little tricky. It says every 6 hours. So first of all, think of T as number of hours. Always good to define your variables, right? And we'll think of Y as a number of bacteria. And then we start with 200. So Y equals 200. And it doubles every 6 hours. So it'll be T over what? Yeah, you don't do 6T, you do T over 6. Because the base will be applied in its entirety once the exponent is 1. In order for the exponent to be 1, you need T to be 6. If you want the exponent to be 2, then T has to be 12, and so forth. And then when will there be 1,000? But you don't have to use T, you can use X if you want to, I don't care. Let's work it out. $13.93. Yeah. And again, I'm not doing graphically. We're going to talk about logs next week, so let's just use logs. So does that make sense? We're okay with that? Okay. Once you guys try example 10, see how it goes. I'll freeze my screen. We'll chat in a couple minutes. Okay. How many days in a year? Good. We'll say 365. Half-life means your base is what? What half? Good. So you want to do scientific notation, guys? It's gonna be very, very small, like just a tiny trace. Here we go. Yeah, so it's a super small trace. We're okay with that one? We're good? All right. Right here, compounding interest. So you guys seen this before? This looks familiar, kind of. Yeah. So if you're compounding means how many times interest is applied to the account, and the number of times you applied interest. Usually it's monthly if you have like an investment account, or sometimes it can be continuous, right? It's always compounding, but it's kind of a trade-off because if you are, because remember what E represents, right? Right, but as a expression, it was 1 + 1 over x raised to the x power over here. So it's kind of a trade-off because n is on the bottom of that fraction, but it's also an exponent too. So it's a bit of a trade-off, right? Like, n's getting really large, so the base is getting smaller, but the exponent's getting bigger, right? So ultimately, there's a convergence. So the difference is not going to be that much between these two types of calculations. So for example, let's invest our money continuously and regularly. Like, so in this case, if we compound monthly, you start at 9,000 bucks, 1 plus 0.025 over 12 raised to the 12 times 5 power. Continuously 9,000, 1 plus, oh, sorry, that was dumb, times E, 0.025 raised to the 5 power. Let's work it out. So $10,197.01. The other one, 10,000. 0.34. So it's not that much. Yeah? It's like $1.33. It's not that much. So anyway, very simple calculation. Okay, that was a lot. You guys are patient. That's good. I promise the rest of the notes are going to be much shorter. Our next test is going to be 2 weeks from today, February 16th, right before ski week. So every day we're going to do a new topic. We will have a date for review on the 14th of February. All the homework's already posted to Schoology. All the answers are already posted. So I got up early this morning, took care of that stuff for you guys. Great. So I didn't want any homework, any work for me for the weekend. So you guys have your tests back. So I think we're in good shape. Homework's right here, guys. You guys have the homework packet already. And basically, you guys doing this entire page here, 1 through 9. That's your homework. I figured it's just wait till the weekend to do it. So, and I think that's it. We're all set. Wait, hold on a second. I'll stop recording.